Good afternoon, everyone. My name is Kavindu and I'm part of the SWT group, and I will be talking to you today about the underwater phase in our mission profile. So here is an overview of what I'm going to talk about. I'm first going to go through the stability condition when floating on the surface of the water, and then I'm going to go on to the diving phase and getting a submerged vessel underwater. And also I'm going to talk about the stability condition during the submerging phase. I'm also going to talk about motion controls using the control surfaces of our vessel, which will be available. And for next week, my next step would be to analyze the equation of motion and perform a trim analysis to find the neutral and critical points of the submerged vessel. So first of all, when the vessel is floating on the surface of the water, from Archimedes' principle, the weight of the water displaced is equal to the weight of the vessel, and the volume of the water displaced will be given by the following equation. V1 is equal to the mass of the vessel divided by the density of the water. For stability, the metacentric height, which is given by Gm, should always be positive. That is, m is always above g. For transfer stability, the positions of V and G should be as shown in the diagram, where V and G are aligned on the same vertical axis. So here is the stability condition for when the vessel is floating on the surface. In terms of the height of the metacenter, which is denoted by Zm, the momentum is given by this equation, where alpha is the tilt angle, and Zg and Zm are the vertical heights of the center of gravity and the metacenter respectively. For the vessel to be stable, the momentum should be negative, which implies that that Zg should be less than Zm, which means that the metacentric height is positive. So in order to submerge, we aim to reach a state of negative buoyancy, which means that the total volume of the air in the vessel should be less than V1, V1 given by this equation here. This means that the upthrust acting on the vessel is less than the weight, and therefore the vessel would sink. So in the design process, the main criteria should be that the total volume of the uncloudable space, which includes the cabin and the cockpit and the space for the systems, etc., should be less than V1, so that the upthrust will be less than the weight. However, in order to control the buoyancy of the vessel, that is, in order to switch between negative, positive, and neutral buoyancy, the total volume of the uncloudable space plus the total volume of the ballast tank should be greater than V1. So here's a summary of the stages during the diving procedure. So when on the surface, we want positive buoyancy when the main ballast tanks are empty. When diving, the main ballast tanks will be full, and we will achieve a state of negative buoyancy. When we reach the required depth, the main ballast tanks would be full, but the trim tanks would be partially filled, and then we'll be able to control the center of buoyancy. And this is called neutral buoyancy. So when the air in the ballast tanks is compressed as they are being filled with water, the vessel will start to sink when the overall density of the vessel is greater than the density of the water. It is important to control the amount of water in the trim tanks in order to keep the center of buoyancy as close to the center of gravity as possible, in order to avoid the momentum caused by the upthrust to rotate the whole vessel. In submarines, the buoyancy and trim tanks are used to adjust the center of balance by pumping air and water back and forth between them. So the moment of gravity is expressed by this equation, and similarly the moment of buoyancy can be expressed by the second equation, and together the total moment will be given by the difference between the center of buoyancy and the center of gravity multiplied by the mass of the vessel multiplied by the gravitational constant. So to keep this, if this moment is a non-zero value, there would be the body would not be in complete mechanical equilibrium and will start to rotate to an orientation where xg minus xb would tend to 0. In a fully submerged body, if the center of gravity does not lie below the center of buoyancy, there will be a momentum that would tend to turn the body so that the center of gravity is lower with respect to the center of buoyancy. And any perturbation from this orientation would be corrected by this momentum, and this is called stable equilibrium. So now I'm going to talk about the control surfaces that are used in submarines. During the diving phase, the vessel should be angled downwards in order to reduce the drag by reducing the effective surface area in contact with the water. Usually on submarines, there are aft and stern hydroplanes in order to control the angle of the dive. For our aircraft, it could be possible to use the control surfaces on the tailplane and the wing in order to act as hydroplanes on a submarine. However, we may need canards at the front of the aircraft to act as the bow hydroplanes. So in practice, submarines are trimmed to be slightly positively buoyant even when fully submerged. And it is the bow hydroplanes that are used to move the submarine up and down in water, and the stern hydroplanes to keep the submarine at a desired angle. So here are some basic concepts of submarines underwater stability. There are 6 degrees of freedom to consider. So these can be split into 2 groups. Bodily translations, which include surge, sway and heave, and angular rotations, which include roll, pitch and yaw. There are some interactions between these motions, however it is a sufficient simplification to treat them in uncoupled groups. So the surge is the outcome of the variation between the thrust on the pump jet and the resistance to motion, the forward motion from the water. And when the submarine is moving, it is these forces should be kept equal and opposite. However, if acceleration or deceleration is required, it can be controlled. The surge smoothing can be controlled by changing the RPM of the pump jet. Yaw and sway is a coupled pair of freedom of motion, which can be controlled by the rudder. The rudder operation affects control of heading and rate of turn by causing the vessel to take up an angle of yaw. Sway is a consequence of yaw, so usually submarines do not have a direct attempt to control sway. Pitch and heave in submarines means pitch and heave is another coupled pair, and submarines control this through the use of hydroplanes. As I mentioned before, the bow hydroplanes control the pitch, and the stern hydroplanes control the heave, respectively. The last freedom, the degree of freedom is roll, and usually submarines do not provide control of roll, because any asymmetric movement tending to cause roll will be countered by the momentum due to the positions of the center of buoyancy and the center of gravity. So for the next week, I will be analyzing equations of motions of a submarine and the stability and control of submarines in the horizontal and vertical planes. I will also aim to perform a trim analysis to find the neutral and critical points of our vessel. That's it for my presentation. I'll be handing it over to Randang to talk about performance.